Okay, hey, let's look at the ratio test today. And the ratio and root tests kind of go together. There are two last tests that we're going to use to prove series are convergent. So let's look at the ratio test today. It says, although the ratio test is not a cure-all for all ills related to tests for convergence, it is particularly useful for series that converge rapidly. Series involving factorials or exponentials are frequently of this type. So if you see factorials, hopefully you'll think of the ratio test because it can be very effective in that. Also, it's another excellent test to use on exponentials. So what is the ratio test? Well, here's theorem 9.17 that goes into detail. It says, suppose we have a series where we are summing up a sub n, the rule of the sequence. And it is defined as so, that the limit as n goes to infinity of the comparison of a sub n sub I said that wrong, a sub n plus 1 divided by a sub n. That generates, what we're seeing there, a sub n plus 1 over a sub n. Well, that defines a ratio, doesn't it? And if you think about it a little bit, I'd have my a sub n term, and then next comes my a sub 1 term. Well, if I take the term from the right and divide it by the term from the left, well, this is like r, isn't it? How do I move from one term to another if it's a geometric term? Well, I multiply by this same ratio r over and over and over. Well, we saw from geometric series tests that if the absolute value, I'm going to use little r, if the absolute value of little r was less than 1, the thing converged. So this is kind of a similar feel to it to me, only we're looking as we go out to infinity. So how are our terms of the sequence behaving when we head clear out to the right? One other thing you're going to note here is that we do use absolute values. So this will give us absolute convergence if they do converge. Because just like the test that we did prior to this where we were talking about conditionally convergent or absolutely convergent, when we wanted to test for absolute convergence, we stripped off, if we had some sort of alternating sequence going on, we stripped that off by throwing the absolute values on. So in a sense, this is what's going on in this particular one too. So taking away, barring any negative action, we will get absolutely convergent. So when do we get absolutely convergent? When this limit of the ratio of two terms turns out to be less than 1. I told you it had a really similar feeling to the geometric series test where the absolute value of r was less than 1. Well, here our limit will turn out to be less than 1. And we will know it's absolutely convergent. If our limit turns out to be a number greater than 1, we know it is divergent. And then the third possibility now is that the limit does equal 1. And in that case, it could be divergent, it could be conditionally convergent, and it could be absolutely convergent. So it will take a different test to go ahead and prove which of those three cases your series happens to be. But that only occurs when the limit equals 1. Before we get too deep into this, I wanted to just review factorials real quickly. 0 factorial is defined as 1. 1 factorial is also defined as 1. 2 factorial we know is 2 times 1. 3, 2, 1, multiply those three numbers and you will get 6. 4, 3, 2, 1 is 4 factorial. That will make us 24. 5 times 4 times 3 times 2 times 1. If I take 24, multiply it by 5, I'm up to 120. 720. And finally, 7 factorial turns out to be 40, so 5,040. It is nice to have a few of those numbers stuck in your head for easy reference. Now, let's save this one and let's go to this 4 factorial over 6 factorial. Would you be able to simplify this rather quickly? Not using a calculator. Well, I know the definition of 6 factorial. It's 6 times 5 times 4 times 3 times 2 times 1. But would I really need to spell this out, 4, 3, 2, 1? Or could I simply replace it with 4 factorial? Well, I could replace it with 4 factorial, and that is, a big advantage on this particular problem. You stop once you get to 4 factorial because then it can cancel with the 4 factorial on top. That gives me 1 over 30. Nice. Let's look at 15 factorial divided by 11 factorial, 4 factorial. 15 factorial, that's a big number. But 11 factorial and 4 factorial, I think will be nice. So let's just leave those. I can see a 15 factorial being a 15 times a 14 times a 13 times a 12 times 11, 9, 8, 7, 6, 5, 4, 3, 2, 1. But that can be expressed as an 11 factorial. And if we do that, we can get 11 factorial cancels with 11 factorial. All right. Is there more work that can be done? Well, sure there is. Let's replace 4 factorial with 4 times 3 times 2 times 1 and take it into some of these top numbers. Well, 4 times 3 is 12, so 12 over 12 is gone. And then I could take a 2 into a 14. 14 divided by 2 gives me that 7. So I'm left with 15 times the 7 times the 13. And if you do the math on that, you get 1365. Okay, those were very concrete examples. Let's move into the ends, which is what we're going to be faced with probably more likely than not when we're doing this a sub n plus 1 and over a sub n. We'll get some things that look like this. Well, if I define n factorial, I'll have n times the next number down from it, which would mean subtract 1, times subtract 2, times an n subtract 3. And this pattern would continue on until I get down to my last 3 terms, 3 times 2 times 1. Think about if I did 7 factorial, I have 7, subtract 1 from it, 6, subtract 2 from the 7, and I'm at 5, subtract 3 from the 7, and I'm at 4, and then I get 3, 2, 1 at the very ending. So just a nice little simple example there. Well, this is probably a lot what we're going to be faced with. Simplifying things with n plus 1, n plus something. Well, n plus 3 would be a larger number than an n plus 1, wouldn't it? So I could write, I'm going to leave this n plus 1 factorial, and now I'm going to decrease my n plus 3 factorial down until I get to an n plus 1 factorial. If I subtracted 1 from this and reduced down to the next lower term, I'd be an n minus 2. Oh, I'm sorry, an n plus 2. Subtract another one, we're at an n plus 1. Whoa, stop a minute. Right there it is. We get n plus 1 factorial. That would take care of the following numbers as we descend. And that just so happens to cancel with our top. And so we could say that this is 1 over n plus 3 times n plus 2 would be the simplifying on that. So just a quick review on factorials before we move into the ratio test. All right, so the question is the series convergent or divergent? And we know that the setup will look like we want to take a limit. We want to look what's happening to our terms far to the right and what the comparison of those terms are. So on the top, we need an a n plus 1. So I'm looking at the term to the right of a sub n. To do that, I'm going to take negative 10, and instead of the power of n, I'm using the power of n plus 1. I just advanced this one term to the right. Okay, this is where it gets tricky. Watch what we have to do here. We're going to have 4 raised to the 2. N plus 1 replaces my n because I'm one term to the right. And then I've got my plus 1. So this n plus 1 is replacing my n. Everything else is staying the same. Here again, we're going to replace n with n plus 1 and then add the 1. And this was a replacement for n. All right, the rule says we have a sub n plus 1 divided by a sub n. That would be the term that I'm looking at right there. So I'm just going to copy this down for 2n plus 1 times n plus 1. I have my ratio built. Top ratio, which is really a sub n plus 1, right? Bottom ratio, which is really a sub n. So I end up with a sub n plus 1 over a sub n. Got it. Let's take that off. Don't forget that this Test has absolute values on it. And now you're looking at that saying, oh my goodness, we're going to want to simplify this thing. Think, huh? Good idea. Okay, the limit as n goes to infinity. If I strip off my, or if I absolute value this, I really don't have a need for the negative because no matter which way it turned out, positive 10 or negative 10 to some power, it's always going to come back to be a positive 10. So I'm going to go ahead and just allow that negative 10 to drop. I guess you could do it now, you could do it later. N, or 10 to the n plus 1 over 4 to the 2n. What I'm doing here is in my mind I'm distributing 2n plus 2 plus 1, so a 2n plus 3. And then times an n plus 2, simplifying right there. Now, you've heard it over and over again. Dividing by a fraction is like multiplying by its reciprocal. So in this case, we want to multiply by the reciprocal of this denominator. 4 to the 2n plus 1 times an n plus 1 over that negative 10. You know, I kind of described what I wanted to do before, but would it be okay if I wrote it like this and brought out a negative 1 to the n times a 10 to the n? Yep, can do that. I think you would agree. Negative 1 raised to any power is going to become a positive 1, absolute valued. So I just am going to write down my 10 to the n. Okay, this has worked out well. I'm going to put my absolute values on there, and then I'm going to ask you to analyze this. Would I need my absolute values any longer? Knowing that n's going to infinity, and n is our counter, it keeps track of what term of the sequence we're on, and those are always positive numbers, either 0 on up to infinity or starting at 1 going to infinity. In our case, n value is starting at 1. So indeed, n's are always positive, and I'm looking where all these n's appear, and they're all positives. I really don't need this absolute value sign here, so I'm going to go ahead and remove it at this stage. It's one less thing that I have to worry about. Now, here's some simplifying that we probably haven't done in a while, but it'll make your brain think. I've got 10 to the n plus 1 over 10 to the n. 10 to the n plus 1 over 10 to the n. Can that be simplified? Indeed it can. I'll come back to it. The other term I have is I have a 4 to the 2n plus 1, and I'm going to compare that to the 4 over the 2n plus 3. Let's see if you can read that. And the final thing I have is an n plus 1 over an n plus 2. Now, I'm showing all this hooked together with multiplication. Maybe I'll make some parentheses to expand on that. I kind of grouped like things together because that's how I'm going to be able to simplify. Next up, the limit as n goes to infinity. Hey, just a quick question. How do I simplify 3 to the 5th over 3 to the 2nd? Well, remember the rules of exponents, you subtract, right? If I have a quotient of two bases that are the same, I take their exponents and subtract them, and I get 3 to the 3rd. Okay, liken that property to what we are sitting with over here. I have 10 to the n plus 1, which I'll subtract the bottom power of n, and would you agree that this just goes to a 10 to the first power? Don't even need to write the 1. Nice. Okay, so we've got that one simplified. Use the same notion. I have 4 to the 2n plus 1, take away 2n plus 3. You can probably already see that I'm going to have a couple more n's on the bottom than what I have on top. Take your negative through, 2n minus 2n gone, 1 minus 3 is a 4 to the negative 2. Yes, indeed. And I think you could see it, that there were more 4's on the bottom. Matter of fact, there were 2 more 4's on the bottom. So this ended up being a 1 over 4 squared. You know, if you really get stuck in a pickle, I suppose you could put a number in like 1 for n, and I'd have 2 times 1 is 2 plus 1 is 3. 3, how does it compare with putting a 1 in the bottom? Well, that'd be a 5 on the bottom. 3 minus 5. Ah, difference of 2 again. Lovely. All right, and then we got this n plus 1 over n plus 2, and no, you can't cancel the n's. All right, this is all about the limit of n going into infinity. And right now, I see no n's in this one, so it would not be incorrect if I wanted to pull 10, looks like 16 sixteenths. If I wanted to pull 10 sixteenths out front and just focus on the limit of the terms with n in it. And so I'm focusing on this. If this is going to infinity, I could say I've got infinity over infinity. L'Hopital's rule would apply. Take the derivative of the top, that'd give me 1. Derivative of the bottom, that gives me 1. It looks like this limit is going to 1. Also, you could say, you know what, the power on the top is same as the degree on the bottom. Highest degree on top is a 1, highest degree on bottom is a 1. Compare the coefficients. The coefficients of these ends are 1. And another reason why this limit's going to 1. I get, for my final answer, the limit of this big ordeal. So the limit as n goes to infinity of a sub n plus 1 over a sub n turned out to be 10 sixteenths. Ooh, we could do better than that. We could call it 5/8, couldn't we? How does that compare with 1? Because remember, the test compares everything to 1. Why, yes, indeed, it is less than 1. And if I look back to my rules, that tells me this ratio is less than 1 or my limit is less than 1. Aha, we're absolutely convergent. Our series a sub n with n starting at 1 going to infinity is convergent. Oops, I should put absolutely. Is absolutely convergent by the ratio test. You know, it's a nice test. The only thing that gets a little bit cranky is the simplifying once you get your terms built. Let's do one another. Here we pick up that factorial, and if you see a factorial or if you see an exponential, and here we have both, this is a good reason to think of the ratio test, okay? They just lend themselves really nicely to that. So let's start it out, the limit as n goes to infinity. What we want to do is create the a sub n plus 1 term, and that would look like an n plus 1 factorial over 5 to the n plus 1. I'm going to divide by a sub n, which is going to be a fraction. So let's just turn it over right now and save ourselves one line of writing. So I'm going to divide by that fraction, which is like multiplying by its reciprocal. Apply your absolute values since it's part of the test. Now I need to know that this is going to equal some limit, right? This is going to equal some L. We got to do the work to get there. So we have the limit as n goes to infinity. All right, now here's where that factorial work helps. Hey, do we need the absolute value signs? I think not. After inspecting each and every term, would these terms all be positive? Yes, they would. So we can allow those absolute value signs just to disappear on us, dissolve them away, and it's all good. So now I need to know, how does an n plus 1 factorial compare to an n factorial? And then I'm going to lump my 5's kind of together, a 5 to the n over a 5 to the n plus 1. Let's rewrite our n plus 1 factorial as an n plus 1. Reduce it by 1. The next one in line is going to be an n, and then it'll be an n minus 1, and so on. So this n will go downhill until it reaches 3, 2, 1. So I'm going to call that an n factorial. Written over this n factorial, correct? And then I have 5 to the n over 5 to the n plus 1. The limit as n goes to infinity. N factorial cancels with n factorial, leaving me an n plus 1. 5 to the n over 5 to the n plus 1 means I have an extra 5 in the bottom that I didn't have on top, right? This is one more than what number of n's I had, or number of 5's I had on top. Okay, so taking this limit The only thing with n in it is really the computation for the limit. The 1/5, if you don't like it inside the limit, you could bring it out front, and n goes to infinity of n plus 1. Well, there's no divisor, is there? So indeed, this limit of n plus 1 going where n is infinity, this would indeed be going to infinity. If I multiply infinity by a fifth, I still get infinity. Infinity is our L, which happens to be greater than 1, and therefore we pick up a divergent conclusion. This series is divergent by the ratio test. You like it? Do you love it? Okay, so I'm up to 20 minutes, and I hope you get the feel for this. If you want me to do one more, I can. So, do we want to do this particular one? Why don't you give it a try? This one does turn out to be divergent. I ended up with, once it's all said and done, see if you can reach this final conclusion that I got 9/2 the limit as n went to infinity of n over n plus 1, which then this would have gone to 1, and I had 9/2 as my limit, which compares that it is greater than 1, and this series also was divergent by the ratio test. Let's do this example number 4. And what it is, you can see that it's a p-series. And I just want to show you how well the ratio test works for the p-series, or maybe it doesn't work very well. So we know the limit test, or the ratio test will just say, you know what, pick up and use the term to the right, which is an n plus 1 term, raised to the 4th, divided by the a sub n term. So we're going to twist this over and have an n to the 4th over 1. Absolute values, because it's part of our setup. Now, we know this simplifies nicely to n equals our n going to infinity of n to the 4th over n plus 1 raised to the 4th. Okay, now what? Well, if I were to expand this, let's start there. I dropped the absolute values because we know this is all positive work, especially because it's raised to the 4th. Anything raised to the 4th is going to be a positive automatically. All right. If I were to expand this, like an n plus 1 times an n plus 1 times an n plus 1 times an n plus 1, one of the terms I'm going to get is an n to the 4th, which is going to be the largest degree out of all of this work, and then we're going to have some descending work, right? We'll get some n to the cubes, n squareds, n to the 1st, along with some coefficients. So I'm going to tell you that stuff's insignificant, and this is my big player, my n to the 4th. Well, if this is a big player, then I'd have n to the 4th over the largest degree in the bottom would be n to the 4th. And the limit as n goes to infinity of the terms with the highest degree in the top being the numerator, and the bottom, the denominator, would be n to the 4th. This is going to have a limit of 1. And hopefully that analysis makes sense to you. But this limit is 1, and that then is this inconclusive conclusion. No determination can be made. And you would have to, no determination can be made. Seek another test. Seek another test of convergence. And the one that we probably would have pointed to all along was, hey, why don't you look at the p-series? Because this is a p-series, right? The power is 4. So if the power is equal to 4, which is greater than 1, then we know that our our series, got a moment there, guys, have a series where it is convergent. by the p-series test. So just wanted to do one where we worked with the p-series. All p-series will turn out to be that way. You know, we could definitely test this out. It would be 1 over n plus 1 raised to some power times this n to the p over 1, limit as n goes to infinity, absolute valued. And once again, the highest power on the bottom is going to be an n to the p over n to the p. You could say it cancels if you wanted to, but mainly the limit's going to go to 1 always on a p-series. So p-series, got to use p-series test. The ratio test is not going to be conclusive for you. Alrighty, we are now up to 25 minutes, and I think that is a great place to stop. This last one does turn out to be absolutely convergent. And if you want to see my notes in class, you could definitely pick up my notes and test it out. But I think by now you probably got the flow of this. Excellent. Hey, have a great day. Ooh, should show you too that you will end up with a homework assignment of these particular problems using the ratio test. All right, now have a great day.